This morning I want to talk about unit vectors, and unit vectors are pretty much exactly what they sound like. Who would like to hesitate a guess at the definition of a unit vector based on its name, because we know how creative mathematicians are in their naming? Anyone? Go for it.
It has a magnitude of 1 unit.
Good. It's a vector, Aiden, with a magnitude of 1. The beautiful thing about the magnitude of 1 is that it can let us do lots and lots of multiples without really changing the magnitude of what we're multiplying by. However, it's a vector. So what does it do when it's acting on something? It doesn't have a magnitude change, it has a direction change. So we can force a vector in a certain direction that we want. It's a bit like your mum saying, I turn you towards the door and push you off to school. She's heading you off into a direction and giving you a magnitude to head out that way. So when we have a unit vector, we find these really, really useful, and we can rewrite pretty much every single vector as a unit vector times a magnitude. We give it a special hat. So it's the vector A, and the little hat says we are a unit vector. Now, if I want to turn my vector A into a unit vector, I have to not strip it of its direction, because we already know when we strip it of direction, we get just the magnitude. I want to strip it of its magnitude. So I get my vector A and I strip it of its magnitude. All right, so it's a bit like what we've done previously where we went, don't worry, absolute value gets rid of our direction. We don't want to do this. We want to strip it of its magnitude. So A hat vector is a unit vector in the direction of vector A. And of course, if we have negative A hat is a unit vector in the opposite direction to A. All right, what this means for us is that if we think of things in terms of unit vectors, we can then multiply them by scalars and we can get new vectors. I'm going to work through 2 examples, neither of which actually use the unit vector, but it's that concept. The first one I want to work through is, let my vector A equal 2 times, oh, sorry, that's why I needed to do it. I and J, that's the bit I hadn't done, are by definition unit vectors in an orthogonal direction. Now, orthogonal is a fancy word for perpendicular. So we've been dealing with 2 very special unit vectors. Now, what's important about saying that they are perpendicular to each other is that, remember, although we tend to make them in the x direction and the y direction, they don't need to be. And in this afternoon's lesson, we're actually going to make them not an x and a y. We're actually going to say this vector gets to maintain its direction, and then the other vector gets to be perpendicular to it. Okay, so I and J can be in any direction. You guys get to decide where the origin is. Often it's very obvious where you want your origin to be. So for this example, we've got our unit vector or our component form, which I know you guys have already been introduced to. -5. So we've got all of our unit vectors up, and we want to find lambda and mu. We tend to use our Greek letters for those scalar multiples in vectors, so that lambda A plus mu b is equal to minus 4i's and minus 1j's. So that's our question. Suggestions on how to go.
Sub A and B in.
Sub our vector a and b in. So I have lambda, and then I have 2i minus 3j's plus mu minus 5i's plus 4j's equals minus 4i's minus j. What do we want to do next?
Equate real and
Sorry?
equate real and imaginary parts.
I like it. We equate real and imaginary parts, yes. But in this context, we're equating all of the vectors in the I unit direction way and all the vectors in the j unit direction way. So how many steps this takes you is up to you. I'm going to really step it out for this example. If I expand by a scalar multiple, I can just use my distributive law. So I'm collecting all of my i's together and all of my j's together. Who wants to tell me how much do I have in my I direction? What's my unit vector times my magnitude in my I direction? It's early, but it's not that early. Anyone? Minus 3? Have I made a mistake? You know I do this. Can we do it? What's the problem? They're multiplied by different things. But can we collect them still? Yeah. How would we collect them still? Bracket 2 lambdas minus 5 mu's times my i's. Who wants to have a go at the next one? Now, I'm going to give you a bit of a hint. You don't have to do this and you'll be correct. But there's a minus outside my j's. So I'm actually going to say minus j. What does that leave me with here? 3 lambdas minus 4 mu's. Now you don't have to do that, you just get these two round the other direction.
Miss.
Yes?
In the exam, do we need to say by comparing the two parts?
Okay, so I love that you're always that step ahead of me. What we're going to do now is compare coefficients. The only thing acting in our I direction is this much. Do you agree? And we know that that has to equal minus 4. So we can write minus 4 equals what was in my brackets. We can do the same thing for my j's, and because we already took out the minus, it actually makes life a little simpler for us. Now, this we do by comparing coefficients. So Emmanuel's question was, do I have to write by comparing coefficients? And I'm going to go out on a limb and say, if you don't, they're not going to dock your mark if that's what you're worried about. However, it's really good practice to write out what it is you're doing. So we are comparing coefficients, and this is where we've got to. Who can solve simultaneous equations? Because that's what we've got. Agreed? 1 and 2. I'm going to give you a second because I'm going to run out of space if I actually do the full working. I'm going to give you a minute to work out simultaneous equations. Who got, if we're not willing to do it, who got 2 for mu? Yep. And 3 for lambda. Okay? So I just want to take this opportunity to say simultaneous equations, not part of the HSC course. Remember, maths is cumulative, and everything that we taught you last year is pretty much fair game as part of a question. Okay? The next question I wanted to do was, if I have a vector v, and it is minus I minus 2j. Now this one, again, we're breaking it up into component forms. We've got our two unit vectors sitting there. If I asked you to find the length and the angle, or the direction, the angle of this vector, what would you do? And what would step 1 be? Step 1? Diagram, thank you. Where, notice we're in our I and our j direction, where is this vector? Quadrant 3, minus 1, minus 2. And that is useful for us to actually see. Because when I now ask you what the magnitude of this vector is, we're looking, Varshan, at a right angle triangle. We've got our two components. How do we do this? Pythagoras' theorem, so we have the square root of 1 squared plus 2 squared equals root 5. Now I can say minus 1 and minus 2, but it doesn't make much difference, and I can see on my diagram I'm 1 and 2. What about your angle? Tan. Tan of, where am I going to put my angle? Here or here? Here? So theta, what's my tan of theta going to be? 2, minus 2 over minus 1, or 2. So what's my angle? 63. And of course, it's in the third quadrant. So what's my actual angle? Positive? Oh, sorry, yes, positive. Negative, thank you. Early in the morning. What's my actual angle? $243. Yep.
Can we express this in radians?
You could if you wanted to. So the question was, can we express this in radians? And the answer would be yes. In the question, they would probably direct you to nearest degree or radians. Degrees tends to work well for vectors because we tend to be resolving them, I don't know, in the real world. We have a better conceptual understanding of, if I said to you, put your hand up at a 45 degree angle, you know what that is. If I ask you what 123 degrees is, you know that we're about out here. We've got a better conceptual understanding than put your hand up at 2 pi radians. You're like, or not, 2 pi would be dreadful, 2/3 pi radians, and you'd be like, oh, hang on. We have good understanding of radians, but we've got a better sort of real world understanding of degrees. The last question I wanted to go through with you is actually a pretty simple one, but I'd like you guys to start by drawing a diagram, and from that diagram I hope that the answers are one line of working. So the question is that A, vector B and vector M are the vectors representing the points. We good?
Miss, why did you ever not see?
Wait a second. You will know once I get the rest of the question. What would you think, M, if I was...
Midpoint.
Thank you. Where M is the midpoint. But the good question of A, B. And then just to make that, just to rub that one in. Alrighty, have a go. Step 1, draw the diagram. Who can give me A? You should be able to almost read it off.
It's 4i minus 7j.
Nice. That's it. Do you want to give me B?
6i plus 3j.
Now, there's a bit of a trick to M, but not much of a trick to M. Diagrammatically, it's quite simple to see where M is. It ends up being about there if you've drawn it correctly. So you can actually work out the coordinates of M. What are they? 5 and -2. So that means our M vector is? If you didn't do it diagrammatically, you've got the midpoint of these two is 5, and the midpoint of these two is -2j. But on the diagram, it comes up very easily if you're at all accurate. Any questions about component form? Because today a unit vector is really a lead into component form, whereas previously I just said to you, we've got these i's and j's in the directions, but they are special unit vectors. We also have a new definition of the vector with the hat, which is the vector stripped of its magnitude and leaving its direction.